Okay, so the next thing we have to worry about is, well, how do we actually determine which pages are supposed to be replaced? That's going to have a great effect, it turns out, on the overall performance of our system. So we're going to look at page replacement algorithms. That's basically determining which pages are going to be swapped out when we need to. We have to choose a victim. And we'll also look at frame allocation algorithms, which basically, when a process comes into play, how many frames do you want to allocate to it? We can actually have that be static or dynamic, by the way. All right, so let's talk about the page replacement algorithms first. So what we'll do is we'll look at a couple different algorithms and we will evaluate them on the basis of the pages that are requested. Now, for the comparisons to be fair, we want the page references to be the same. So we'll call that the sequence of page references, we'll call it the reference string. And in the examples we're going to look at, mostly are going to use this page reference string. That is, as the program runs, you're going to have a series of addresses that you want to access. The first address you access is going to belong to page 7. The second page we access is going to belong to page 0, and so on and so forth. So that's going to be a string of page numbers. We're not going to worry about the full addresses, about the offsets to the pages, anything like that, because the offsets don't affect page replacement, because you're always bringing the pages in their entirety. Now, it stands to reason as you decrease the number of frames you've allocated to a process, that it's going to become more and more likely that you're going to have a page fault. For example, in the diagram here from the book, if you only had one frame, then basically you could only have one page in memory at any one time. So anytime you got a reference to a different page, you'd have to have a page fault. So you get lots and lots of page faults. As we increase the number of frames, the amount of memory that we've allocated to a particular process, then the number of page faults is going to decrease, because more and more of the pages of that process will actually be resident in memory. So it'll be less and less likely that you'll get a page fault. So let's look at one of the simplest algorithms for page replacement. That's the first in, first out algorithm. So the reference string here, 701, blah, 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 and we've got we'll assume we only have three frames of memory that we can work with. And so the way our diagram works here is that we're going to show our frames as kind of running vertically here. So we've got frame 1, frame 2, and frame 3. And the contents of what's in that frame, in this case in frame 1, are going to change over time. So each column indicates what the world looks like, what the page table looks like with each reference. So with this reference here, the contents of the page table are, well, I got frame 7, frame 0, and frame 1 are listed in our page table, and so on and so forth. So here's an example for that. When we first get the reference string, we have nothing in the page table. So we have 3 frames we can work with. So we're going to take our page number 7, we'll swap it into the topmost element here. When we get to the reference for page 0, it's not in the memory here yet, so we go ahead and we swap into a free space here, the next one, so that swaps into the 0 from the hard drive. When we get the access for page 1, that's not in this memory over here, so we have to go ahead and swap it into a free space, this free frame, so now we have 701. Now we have a request for page number 2. 2 is not resident in the memory at that time, there's no 2 in here. So because of no 2, we have to select a page for replacement. We are just using a FIFO replacement, which means the first one in is the first one out. So 7's been in the longest, so it gets swapped out, and we now swap 2 into the frame 0. So now you have 2 over here. When we get the access to frame 0, there is no frame fault because 0 is already in the memory. So no page fault. Happy days. Then we have a request for page 3. 3 is not in the memory at this time. It's not in the page table. So again, FIFO. So we go to this one that's been in the longest. You can see 0's been in here for 4 steps actually. So we swap 3 in to the location where 0 was. So now our memory is 2, 3, and 1. And this process continues on. You can kind of see a pattern here. Every time there's a page fault. So we had a page fault here, a page fault here, page fault here to fill up the initial table. Then we had a page fault over here. We had a page fault over here to fill that in. Page fault over here. You just kind of get this nice sort of zigzag pattern. There was a page fault for that one, a page fault for that one, a page fault for this one, a page fault for the 0. Now though, we have an access to 3, 3's in memory, 2's in memory, so no page faults there. But when we get to 1, it's not in memory. We continue our pattern down to the 1 and so on. You can actually count the page faults here. I've got 1, 2, 3, 4, 6 more is 10, 11, 12. So I have 15 page faults that occurred using a FIFO replacement strategy with only 3 frames. So let's try the same thing again. We'll do it with 4 frames. And I'm going to drop out of this, switch over to my spreadsheet, and let me just copy this over here, and let me select all these so they're the right size. Otherwise it'll be hard. There we go. All right. So here is the same table we kind of looked at before. Make it a little bigger for you. And so here's our reference string up at the top. Now we've got 4 frames to work with. So I'll go ahead. The beginning is going to be the same. Page fault there, necessarily. Page fault there. Up here, another page fault, 7, 0, and 1. Up here, 7, 0, 1, and 2. All right, now you've got a 0. That's already in the memory, so no problem there. There's a 3 that's not in memory, so we have to do a page fault. So we're doing FIFO, so we can look here and see that the 7's been in the longest, so we get rid of that. So that goes away. Then we have 0, 1, and 2. 0, no page fault, happy days. Here there's a page fault, so we have to replace the one that's been there the next longest, which is the 0. So put a 4 there, 1, a 2. No page fault for the 2, no page fault for the 3. Over to the 0. So for the 0, we're down to replacing this guy here, so the rest are going to stay the same, 3 and 4. No page fault for the 3. Here's no page fault for the 2. Here's a 1. So that's this guy down here needs to be replaced. He's been there the longest, so we get 3, 4, and 0. Now we have a page fault for the 2. Unfortunately, we just got rid of the 2 here. Darn it, so it goes. So we're up to this guy for FIFO, so put the 2 in there, and the 4, the 0, and the 1. 0 we're good, 1 we're good. Here's the 7. 4's been there the longest, so we'll start by swapping that one out. 0, 1, that stays a 2. No page fault for 0, no page fault for the 1. So the total number of page faults, 4, 5, 6, 7, 8, 9, 10. So fewer page faults because we increased the number of frames, and that's typically what you'll see, although not always, as we'll see in a second here. So back to our PowerPoint slide. It turns out that actually there, in certain cases with FIFO, there is something called Belady's anomaly, where actually when you increase the number of frames allocated to a process, you can actually increase the number of page faults. Seems kind of weird, I know, but let me show you an example of that. Let's see, that's over here. So we're going to consider this reference string up here, 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. And here is the FIFO table for 3 frames. You can count the number of page faults. You see 1, 2, 3, 4, 5, 6, 7, 8, 9 page faults. Now we'll increase this to 4 frames. Do the same exercise, run through this again. Make sure you can do this on exams, by the way. And you'll actually see the number of page faults has increased from 9 to 10. Seems counterintuitive, which is why it's called an anomaly, but it actually can happen here. You can kind of see what's going on in this sequence over here. Basically, we always, here when we had a page fault for 5, let me make this a little bit bigger for you so you can see. When we had the page fault over here for the 5, we removed the 1 to place the 5 into play. On the very next reference, we needed the 1. So we kicked the 2 out and replaced it with the 1. But on the very next reference from that, we needed the 2 that we just got rid of. So basically, it's like we're always just off by 1 in terms of which page we choose to swap out, always swapping out the page it turns out we're going to need on the very next reference. So that's like the worst case. So that's Belady's anomaly. And that's kind of what this table shows here. It's for this reference string with different numbers of frames and counts the overall number of page faults. You can see right here when we went from 3 frames to 4, the overall number of faults went from 9 to 10. In general, though, of course, this is anomalous behavior. Usually as you increase the number of frames, you're going to be decreasing the number of page faults. Okay, so there actually is an optimal algorithm. The optimal algorithm is optimal in the sense that it minimizes the number of page faults that can occur for any number of frames. It turns out that 9 is going to be optimal for a particular number of, I think it's for 4 frames. And the the trick here is that this is not actually a realizable algorithm, because we don't actually know in reality when the page will next be referenced. We have no idea about that. All we know is what's happened in the past. There's no guarantee. We have no crystal ball to look in the future. So this theoreticians refer to this as being an oracle. It's an oracle algorithm. It's not realizable, but it's very useful in terms of measuring, as a benchmark in measuring the performance of other actual realizable algorithms. So here is the optimal algorithm being used on our reference string as before. So just kind of point out here what's going on. So we get our usual 3 faults up at the beginning. So we get the 7, 0, 1. Those all have to call page faults. When we get to the 2, so 2 is not resident in memory, so we have a fault. So we look at the 7, 0, and the 1. Here's our crystal ball. We know what all the page references are going to be, which would not be the case in a real world, but here we do. And we can say, well, so look for when is a 0 going to be? It's going to be used pretty soon. When is a 1 going to be used? Well, the 1's over here, but the 7's not going to be used until way over here. So that's the one that's is sort of most pushed off into the future for when we're going to need it. So we're going to choose to swap that one out. So we swap the 7 out and put the 2 in. Now the 0, no page fault. 3, we have another page fault. Our current page table looks like this. So again, you'd look, when is the next time we're going to need a 2, a 0, or a 1? Well, here's a 0. Here's a 2, so the 1's way over here, so we're going to swap the 1 out. So the 1 gets swapped out and the 3 gets swapped into that place. Now we have the 0, no page fault because it's already in memory right here. But here's the 4. So you'd look at the 2, 0, and the 3 and determine which one of those is going to be used most distant into the future. Well, here's the 2, here's the 3, here's the 0. Turns out they're actually all pretty soon to be referenced, but 0 is the farthest one out, so we'd swap that out and bring the 4 in. So you continue along like this, pretty straightforward. Always looking to the future to see which one you're going to swap out next. And you can see here the total number of page faults is 4, 5, 6, 7, 8, 9. And so that is the minimum number of page faults that you need to service this particular reference string over here. A nice exercise might be for you guys to go ahead and run this for 4 frames to see if you can calculate the optimal number of page faults for that. All right, so back to algorithms which we actually can realize. So here we've got the least recently used algorithm. The idea here is you basically have, in a sense, a timestamp associated with each page. And you're going to, when you have to replace a page, you're going to use the page which it's been the longest since you used it. It's the most distant in the past that you've used it. So we can just associate a time with each one. So let's take a look at the reference string for that. So here we've got the 7, the 0, and the 1. We always get the 3 page faults at the beginning. And we get to the 2. So you look at the pages that are in there, the 7, the 0, and the 1, and you say, when were they most recently accessed? Well, just look backwards on the reference string here, and you can see that the 7 is the one that was accessed most distantly into the past. So we choose to replace the 7 with a 2. So swap the 7 out, swap the page 2 in, and we're good to go. Get to the 0, no page fault. Get to the 3, there is a page fault because the 3 is not in memory here. So again, you have to look backwards. You say, well, when's the most distant one? Well, you can see it's the 1 because here's the 0 there, the 2 is here. So the 1's the most distant, so we'd swap that one out. So that would go ahead and bring a 3 where the 1 was. Now let's do one more. 0, no page fault. 4, there is a page fault. So again, you look backwards through time. You can say, well, of the 3 guys that are in memory here, there's the 0, that's pretty recent. There's the 3, that's pretty recent. So it must be the 2 that's the most distant. So you swap the 2 out and swap the 4 in. You get 12 page faults instead of 9. It's better than FIFO, which I think gave us like 15 or something, but it's worse than optimal, which did 9. So in general, this is a pretty good algorithm. It's used in a lot of operating systems, but how might you go about implementing this? Because of course here it's really simple. You've only got 3 entries in your page table, but in a real operating system, the page tables can be very, very large. And so you may have, for each of those entries, you've got a different timestamp. And so finding the value on your page table, which is the smallest, or the smallest as a timestamp, can be costly. There's some computational time. So there's kind of different ways that you can do this. I'm not going to go into these in too much detail. The book goes over them fairly well. One way to do this is to use a stack. you can implement these using a stack, and basically this, when you reference a page, you move it to the top of the stack. So if pages aren't referenced for a long time, they tend to percolate down to the bottom of the stack. So if you're doing kind of a FIFO activation with the stack, that can work quite well. The problem with the stack implementation is you do have to find the page that you're accessing when you access it someplace in that stack. So you may have some pointers you have to manipulate to make that work, but it can be done. By the way, least recently used and optimal are both implementable via stacks. And with stack algorithms, just kind of this general behavior for schedulers that they do not suffer from Belady's anomaly. And I'm not going to go over this, but you can see kind of what the stacks look like. And go ahead, follow this example in the book. All right, so the next thing I want to look at is the least recently used approximation algorithm. So one of the difficulties with least recently used is just the runtime and accessing the stack if we're using that, or accessing the timestamps and sorting things. You could use priority queues, but that can be a little costly. So in general, we can use just an approximation of least recently used. So the way that we can do that is we can have some kind of bits that we associate with our page table called a reference bit. In the simplest case, what you have is a single bit that you allocate in the page table, and whenever you access a page, you set its bit to 1. Every so often what you could do is you could clear all the bits to 0. And so over time, bits will be slowly being set from 0 to 1. When you first bring a page into memory, you'd go ahead and you'd set the bit to 1. But what will happen is, at any particular time, if you need a page to swap out, you're going to look for that page whose reference bit is 0, because assuming that the clearing of all those bits was a while ago, what you know is that all the ones that have been set to 1 have at least been accessed since the last time the clock ticked and you cleared all the bits to 0. And so you're usually well enough off to select a bit who's select a page whose reference bit is 0 and choose to swap that one out, because more or less it hasn't been accessed for a while. You can add more bits to improve your approximation of least recently used. So for example, you can use a technique called a second chance algorithm. And what you do there is you use a clock replacement scheme. I'm going to show you a diagram in a second that shows this off. But again, so the same basic idea. You're going to be looking at the reference bit. If it's 0, then that's somebody you're willing to replace. If it's 1, though, then what we'll do is we'll set that bit to 0, but we won't swap it out, and we'll go on to the next page in the list to see, is that one we want to swap out. So here's a diagram that kind of shows how that would work. So here's our page table, or really just the reference bits of the page table. And you basically have to keep a pointer into the page table, which is just going to circulate around and around in a loop. That's why it's called a clock algorithm. Let's say that we need a page replacement. So we look at this guy in the page table, and his page value, his reference bit, is set to 1. So he's been accessed somewhat recently because we set the bit to 1. So what we do is we set that bit to 0 and we move our pointer down to the next element in the page table. Well, his bit is 1 as well. So we set that bit to 0. We move to the next element of the page table and his bit is 0. That gives us this picture over here on the right-hand side of the page. So that is the page we would choose to swap out. Swap him out, swap a new page in, and set this bit back to 1 over there in that case. So that's a sort of a standard counting algorithm, that second chance algorithm. Another flavor algorithm we can use is, the book calls it least frequently used, although I think it's a bit of a misnomer. What the book says, you keep a counter associated with each page. You count how many times the page is referenced. So when you have to, every time you reference a page, you increment that counter. When you need to choose a page for replacement, you choose the page whose counter is the lowest. Now, really, this is not a frequency because it's just a counter. So a better name for this would probably be the least used page. A problem with this algorithm is that if during the execution of your program you access the page a whole bunch of times at the beginning, early on in the execution of a program, then its page count will be very, very high. But it could be that many, many hours have passed since the program was loaded. You haven't accessed that page ever again, but you're never choosing to swap it out, because its page count is so high. You're always swapping out these other pages, and that's typically not a good thing, as we'll see. It turns out there's this working set thing, and so you remember I talked about locality again. So if a page isn't being accessed for a very long time, it's probably not in the locality of the program, and we'd be better off swapping it out. In the programming assignment I give you, I actually have you implement a real frequency. That is, you keep track of both a numerator, which is the number, which is the count we have here, but then the denominator will give you a ratio. And the denominator is basically the total number of page accesses or references that have occurred since that page was first loaded into memory. That'll give you a real frequency. So the flip side of what the book calls least frequently used is the most frequently used algorithm. And it seems a little counterintuitive on the face of it, but what you choose to do is you choose to swap out the page with the smallest count. And the idea there is that typically when a page is first swapped in, its page count will necessarily be very low, only 1. You don't want to typically swap out a page you just swapped in. So the argument here is by using most frequently used, you're going to tend to swap out pages which hopefully have been around a long time but haven't been accessed all that frequently. It's a bit of an argument about which one's going to be more or less effective depending on your reference string that you have. Okay, so there are some techniques you can do to try to ameliorate the number of pages that you have to swap in and out. You can keep pools of free frames that are kind of always available. So what you do is you basically always want to make sure you have some free frames around, so you don't need ever to swap anybody out when a page needs to be swapped in. And the way you do that is kind of you wait when the CPU has some free time, you try to select a frame for whatever, through using whatever algorithm you have, and swap it out, thus creating a free frame. And this is, again, you would do this when the CPU would be otherwise idle. And if you can do that, then there's always sort of a collection of free frames. You never have to worry about a swap out. And you could use your modified pages to the thing you do. You look at pages that have been modified. Again, if you have idle time, you could choose not only to swap out, but to basically update the copy of the frame of the page, which is currently sitting in a frame, and just copy that onto the hard drive, so that now what's on the hard drive and what's in the frame actually match. And then you can set the dirty bit. You can clear it up again, and then hopefully, if you do need to replace that page, you won't have to swap it out. So a bunch of things like that you can do to try to decrease the number of swap outs that you have to use. Okay, so we looked at page replacement algorithms, and now we're going to look at the original allocation of frames. So when a process first is going to be loaded into memory, typically you need to decide how many pages or how many frames to allocate for that process. In general, there's a minimum number of frames you have to have, because you may have instructions which might possibly need to access all of those pages simultaneously. So for example, on the IBM 370, an old machine I actually worked on back when I was in college, they had an instruction called an SS move, machine code instruction, which might need to access up to 6 pages simultaneously. This is kind of a big block move thing. So in that case, the minimum number of frames you need to allocate for that process would be 6. You could never have fewer than that, or if you had to do that process, you might be stuck in an infinite loop of having to do all these page faults over and over again in an endless cycle. The maximum number of frames you could allocate to a process is basically all of them, so all the frames in the system. You probably don't want to do that, because then no other processes can run the system at the same time. So there's basically 2 allocation schemes, basic ones. There's fixed allocation, where you basically choose up front how many frames to allocate to a process, and you allocate them, and then it's just up to our page replacement algorithms to determine which pages are actually resident in that fixed set of frames. Or you might have a priority allocation scheme, and there be lots of variations in between. For fixed allocation, it's fairly straightforward. You might have sort of just an equal allocation where you say, well, there's 100 frames in the system, and so if there's 5 processes, I'll just allocate 20 frames to each one. You probably want to set some frames aside for your free frame buffer pool that we talked about before. You could also use a proportional allocation scheme, where you look at the overall size of the processes and you divvy up the number of frames you have proportionate to the overall size of the process. The idea behind that is, if you're a great big process, you're probably going to need more frames overall. You'll be accessing more pages more rapidly, And so you might want to have more frames allocated just to cut down the overall number of page faults that are going to occur. And this is just a simple example here of how you can do the calculation for the size, but it's a simple proportionality equation. Priority allocation is, rather than relying on size to determine how many frames are allocated, you have some kind of a concept of a priority. And so here what you might say is higher priority processes should be given more pages because I want to have fewer page faults occur to those processes. I want them to run faster, for some example. In terms of allocation schemes, you can either global or local schemes to do that. A global scheme is going to be selecting replacements from the set of all the frames that are in the system at any one time, not just those frames from among those frames that it has access to. So that is, if you're using global replacement, then one process may choose to swap out a page belonging to a different process and basically take over its frame. Local replacement, you're only choosing to swap out from the frames that you own. So if you're using global replacement, then actually the number of frames that are allocated to a process may change over time. All right, so non-uniform memory access. I'm not going to talk about this very much, but in modern systems, the speed of access to memory varies a great deal. That is, you can't say that the amount of time it takes to access memory is fixed. It may change depending on where in the memory you're doing the access. It may even be that you have sort of different tiers of memory, of different RAM that you're going to use. And so that's obviously going to make the calculations for your effective access time much more complicated, and it's going to make the replacement algorithms also a lot more complicated. But I'm not going to go into that too much detail at this time. You can go ahead and read about it. All right, so I want to move on to thrashing. So thrashing is when a process doesn't have enough pages and their page fault rate commensally becomes very, very high. So think about this. Let's say that a process is routinely needing to access 4 pages, but we've only allocated 3 frames for that process. In that case, it's going to be very likely, maybe 1 in 4 accesses, that there's going to be a page fault. And so you have to bring in another page. Or sorry, 1 in 3 actually. 1 in 4. You'd have to swap out one of the 3 that you've got in, bring up another one, and so on you'd go. So you'd have lots and lots of page faults occurring. Now, if you're doing page faults, remember, that's basically an I/O operation. And so when I/O is going on, you're not doing any CPU work. Now, if you've got other processes, you can go ahead and use those and run those processes instead. So you may keep the overall CPU usage fairly high, but in terms of progress being made by a process which is thrashing, it's probably not making almost any progress at all. It's running a few CPU instructions, doing okay, and then there's a page fault. Eventually, it gets a context switch back. It runs a few more instructions, and there's another page fault. So nothing much is very happening. You can even get into a situation basically where every process is thrashing, and then you have real problems. So here's kind of what that means. As we increase our degree of multi-programming, so we're putting more and more processes into the RAM, we have to divide up our fixed set of frames, our physical memory, into smaller and smaller pieces. That is, we have fewer and fewer frames allocated to each process. Well, that's okay up to a point, but eventually, if a process gets too few frames, then it's going to be very frequently having a page fault, because it's going to need a page that is not resident in one of its very few frames to go get the page and bring it into memory. So what you'll see is the CPU utilization will basically increase as you increase the degree of multi-programming. The CPU will stay very busy. Basically, when one process is doing a page fault, it'll be able to spend useful time executing instructions for another process. But as we keep pushing this, we kind of reach a breaking point, kind of get a plateau, where if we increase multi-programming anymore, we're basically decreasing the number of frames that are allocated to every process, and all of a sudden every process is spending most of its time waiting for a page fault, and our CPU utilization drops off a cliff because we're basically just spending all the time waiting for the page faults to be serviced, waiting on the disk all the time. Tons of I/O and no real CPU going on. Okay, so why does thrashing occur? And why does demand paging work very well? Well, they're related. So I mentioned earlier on the concept of a locality model. That is, it turns out if you look at memory, of what memory is accessed when a process is running, it's going to turn out that in general, when a process is accessing a set of pages for one instruction, it's probably going to be accessing the very same set of pages on the next instruction it has to do. So that in general is very strongly correlated over lots and lots of experience, looking at lots and lots of processes. That's typically how they work. Now, eventually, when a process is running along, it's going to move to a different locality. For example, it may call a subroutine. The code for the subroutine is located in a different page. Could be the data that's associated with that subroutine is in a different page. And so that's a different locality. You kind of switch to a different locality. Localities may overlap, but they can occur. When does thrashing occur? Well, thrashing occurs when the overall size of the localities of all of the processes which are currently running in the system exceed the total memory in the system. That is the total physical memory that we have. If that occurs, then that means we're going to get thrashing. Here is an image which I hope will kind of make you understand what locality means. So this diagram is taken from the textbook, and the x-axis here shows execution time. And once you can think about each each column here, they're very, very thin little columns. The y-axis indicates addresses of memory. So if you see a dark smudge up here, what that means is in this slice of time, let's circle this, look at this line here. And this slice of time here, whenever that was, maybe this stands for like, I don't know, a millisecond worth of execution. These addresses were accessed. So whatever, 34, this is probably 34,000 down to like 33,500. None of this space in this memory was accessed. Get all the way down here, and maybe you access down here, a little bit of the memory addresses down here and down here. So this indicates the locality. If you look at any one vertical stripe, that's the current locality of the program. The green arrows here indicate where there was a locality shift. So you can see at this point here, you had this locality to the left of the green arrow, and to the right of the head of the green arrow, a very different set of regions has been marked. So that was a locality shift. Again, with this green arrow, we shifted from kind of this locality shown here to this locality shown up here. And of course, there's also locality shifts happening down here. So again, one vertical beam through here indicates the locality at a particular slice in time. So the localities can shift over time. So what we want is we want the pages which compose the locality to be the current locality to be resident in memory, to be in the RAM, because if they are, there's no page faults. The locality is already in memory, then we're likely to, as long as we stay in that locality, we're just accessing the pages that we already have in memory, and everything's hunky-dory. The problem is we don't really know what the locality is. We can just try to approximate that, and to do that we use something called the working set model. So a working set window is a number of page references. So for example, you might look at the previous 10,000 instructions you've executed, and your working set would be all the pages that you accessed during the last 10,000 instructions. And you say, well, that's my working set. Now that may or may not be the locality. If you make the delta very small, so maybe you only look back the previous 100 instructions, well, that may not be the actual entire locality. The locality might be larger than that, and maybe a larger space. Again, you kind of look over here. Let's go back to our diagram. If you looked at, say, this part maybe here, I'm going to go back again. If you look at the locality, if you look at this time slice here, you might say, I'm going back just 100. Well, that might be this little piece here. That might not capture the entire locality. It may turn out the locality is actually this larger chunk of pieces over here, because even though I'm only accessing these guys here, I'm about to access one of these values over here real soon. Just don't know it yet. So you don't want the delta to be too small, because then it might not be big enough to hold the entire locality that you're working in. You don't want the delta to be too large, because if it's very large, then you're actually not providing a particularly good approximation of the true locality. It could be encompassing several localities all at once. And that again would be, if you went back to the previous example, instead of this being a very thin line, imagine the line being very fat, and then go over several localities all at the same time. And of course, if you made the locality infinite, that's just encompass the entire program. That's not very useful at all. So we can talk about this value D as being a sum of the working set sizes, the working sets of all the processes which are currently in memory, and that's going to be your total demand for frames. So the working set size, the number of frames that each process needs, you add that all up, that's going to be your total demand for frames. What we want to watch out for is if our D gets bigger than M, the total number of frames we have in the system. If that happens, then we have thrashing. So what we want to do is, if we kind of watch D every so often, if the sum of our working sets gets too big, then one of the things we can do is we can suspend one of the processes, kind of remove it from the system, swap it out, suspend it, swap it out, and that will basically free up the frames that it has. We can then allocate those frames to the processes which we've left in memory, and hopefully that will then remove the thrashing. The D will actually have decreased some, and we should be better off then. Here's another diagram from the textbook, and it kind of shows what the current working set is. So if you kind of look at the page reference string up here, so I look back here in time, you can say, well, if this is the delta, then you can say, well, I have access to 2, a 6, a 1, a 5, a 7 a bunch of times, and so my current working set here is 1, 2, 5, 6, 7. And later on, as the reference string goes along, here's my delta. You look at all these guys, you can see, well, the working set's much narrower here. It's just pages 3 and 4. That's the working set there. So the working set's cool. We want to keep track of it. So how can we do that? Well, one of the best ways to do it is to use a timer in combination with a reference bit for our pages. So if we went ahead and say, well, let delta be 10,000, so we'll look at the previous 10,000 references. So what we'll do is we'll keep 2 bits, and we'll have our timer will trigger every 5,000 time units. Whenever there's a timer interrupt, what we'll do is we'll take all the bits in our least order of the 2 bits, and we'll copy those bits into the higher order bits, and we'll set all the low order bits of the 2 bits to 0. So you'll have basically all zeros in the extreme right hand bit, and then a mix of 1s and 0s in the left hand bit. The 1s will be those that were accessed in the previous 5,000 time units. Then whenever a page is accessed, we flip that least order bit to 1. When we need to select a page to be swapped out, we look for an entry for whom both of those bits, the upper level bit and the lower level bit, are both 0. If they are, that's something that hasn't been accessed probably in the last 10,000 time units. And so we say, well, that's not in the working set. We'll choose to swap that out. So that's the basic concept. Fairly straightforward. You can actually do a better job, a more accurate job with that. If you partition this up a little bit more, instead of just 2 bits, what if you use 10 bits? And again, you have every 1,000 time units. One of the problems with the 2-bit scheme here is it's very coarse, and so it may be that you've accessed a page, but it was 9,999 accesses ago, so its higher order bit is actually set to 1, its lower bit is set to 0, and then you may have a page which is accessed 5,001 units ago, and they'll look exactly the same in terms of their bits, but it's not a particularly accurate representation of the working set. So we can do better if we increase to 10 bits and do interrupts every 1,000 time units. Again, just a copy shift bits to the left, always making the rightmost bit 0 and shifting bits to the left. Okay, so another thing you can do is you can try to dynamically watch your page fault frequency and manipulate your the number of frames you've allocated to processes as a way of trying to keep the page fault rate in kind of a nice location. So what this diagram from the book shows is you kind of set an upper bound for the page fault and a lower bound for the page fault rates. Why would you worry about a lower bound? Well, because with you want to try, typically, especially in a server environment, you want to try to have as many processes in the system as you can. That is, you want to have your multi-programming level being very high. But for multi-programming levels to be high, you then have a commensurately smaller number of frames that you could allocate to each process. So what we do here is we look at our upper bound. If our page fault frequency is too high, we're getting too many page faults, and we say, well, we've exceeded our upper bound, and so what I'm going to do in that case is I want to decrease the number of page faults that are occurring. So I want to increase the number of frames that are allocated to each process. So I want to decrease the degree of multi-programming in that case. So I could swap a process out and then share the now freed frames among the remaining processes. If the number of page faults gets too low, that means I could actually stand to increase my multi-programming. Thus, I can decrease the number of frames allocated to each process, which will increase their page fault rate. But as long as we kind of stay in a sweet spot here, our CPU utilization should stay very high, our page fault should stay kind of in a range that we're happy with, and so that would be a good thing. This again just kind of shows the concept between a relationship between the working sets and the page fault rates. So you can kind of look at page faults occur as working sets are brought in. Once the locality is the working set, then you get very low page fault rates. Here you get another spike, you're probably switching to a new locality. Once those are swapped into the working set, then the page fault rate will drop off again. Other things you might worry about with virtual memory is prepaging. So what you might choose to do is when a process is first brought in, instead of bringing just 1 or 2 pages, bring in a whole bunch of pages all at once, maybe the first 100 pages or something like that of the process. And hopefully those block transferal of data from the hard drives will be much faster than doing that like 100 one-page accesses to page faults to bring them all in. So that can help. Another thing you can try to do is you can try to somehow determine bring pages in kind of before they're needed. So what you might do there is you might say, well, I'm using page 1, so let's say page 15. What I'm going to do is I don't see page 16 is in memory yet, so let me bring in page 16 just on the off chance I'm going to need that one next. So you can go ahead and try to guess which ones are going to maybe need to be used next. Now, the downside of that is you might pay the cost for bringing page 16 into memory, and then it turns out you didn't actually need it. So there you paid for some work that you didn't need to do. So you got to kind of weigh off the cost of doing the paging, which might be wasted, the pre-paging, which might be wasted, versus the potential savings you'd have in not having to have a page fault because you already brought the page into memory. Another thing we can worry about is page size. On some operating systems, the designer can actually choose the size of the pages they're going to work with. And actually, a lot of modern hardware systems, the MMUs actually provide for multiple size pages. And so the operating system might want to take special advantage of that. Now, of course, if you're using different size frames or different size pages, then you have to worry about internal fragmentation, because if you're using great big frames, you have more internal fragmentation. You might, if you have lots of smaller frames, your page table is going to get very large. You have to pay the cost of storing that page table. That uses up memory just to store the page table, and so on and so forth. So there's a lot of kind of little things that can come into play when you're working with different size pages. But keep in mind, there are always going to be powers of 2, because that's going to make it easy to do the calculation. Other issues you can have is just sort of the access to your lookup tables and how fast that's going to be. It's called TLB Reach. Go ahead and take a look at the book of that. I'm not going to talk about it very much at this time. Okay, so here's another problem you can run into with paging. In fact, I had a student who ran into a problem very much like this recently, a graduate student. So assume you have a program which has an array, has a two-dimensional array, 128 values each way. Each row can be stored on one page, and the program is only allocated a single page to do its execution. So look at the first piece of code here, and what you'll see is that the fast-moving term is the J term over here. That's the row, so that's the column within a particular row. So the way this is going to run is we're going to be changing the column number very rapidly. And so what will happen is the first time you want to access the 0th element, the 0th column of a row, you'll have a page fault. You'll have to bring that row into memory, but then you'll be able to go through this inner loop without any more page faults. So you'll just have one page fault. When I increments from 0 to 1, that's the next row in our array. And so we're going to get, when we come here with I now equal to 1, you're going to have another page fault. So it stands to reason you're going to have a page fault for every iteration of this outer loop, but no extra page faults for the inner loop over here. So you have a total of 128 page faults. Now, all we do is we basically change the order of our first two of our for loops here. So we're going to iterate the slowest is going to be the column. We're going to iterate the rows the fastest. So you can see what's going to happen. First axis over here, of course, we'll get a page fault. But the next time we go through this loop, we're going to want to get to the next row because we've changed I to the next row. That's going to be another page fault. So we're going to have a page fault every single time we execute this inner line here because you're going to a new row each time, and you can only hold one row in memory at a time. So that's going to lead to this 128 squared 16K page fault. So the code isn't very different, but the program's going to run much, much more slowly because you're going to have so many page faults. I mentioned before I had a student who ran into trouble like this. He had a long-running program that uses a large data set, basically a very large array. The array was so large it couldn't all be held in memory at the same time, so it was using virtual memory. What happened as the program ran is that the data that was stored in the array originally was all clustered down in the low end of the array, from indices like 0 up to 1,000,000 or something like that. But as the program ran on, those million elements got scattered over more and more, over a broader and broader area of this overall much larger array. Say it had like 1 billion entries in it. And eventually what happened is that most of the pages only had one entry that was being used. One portion of the array was being used. So as the program ran, it was having to access 1 million different pages. A whole bunch of pages were having to be accessed, and there's no way they could all be kept into memory at the same time. So basically, we watched as it ran. After several hours, the program just got unbelievably slow. It didn't run anymore. And eventually, we figured out what was happening. The program was basically thrashing. We could actually see the page fault rate getting really, really high. So we knew that thrashing was going on. So we looked at the problem and we decided, okay, well, the issue here is we're going to do our own compaction. So instead of allowing the elements to get scattered over this very large array, instead basically allocated his own array, allocated a portion of memory, and did the memory management himself. So he always stayed clustered in basically the million elements always stayed clustered in the same set of pages. And then the program ran just fine. All right, another thing you have to worry about with paging, I'm not going to talk about this too much, is I/O interlock. Sometimes if there's an I/O process is pending, you've asked for an I/O process to occur, you can't afford to swap out the pages that are associated with that I/O operation. Basically, you have to freeze those in memory until the I/O operation can complete. So as an example, consider that you had a buffer that you'd set up, and you wanted to get some values from a disk drive and place it in the buffer. So you send out the request to the disk drive. It may take a while for the disk drive to get around to answering that request. Under no circumstances do you want to swap out these pages, because if you did that, the disk drive would have nowhere to put its results, and you would have sacrificed all the time you spent waiting for that disk drive. So that's an I/O lockout. There's some ways around that, but using double buffering and stuff like that, we won't talk about that. Okay, so that's the end of Chapter 9.